Let's close off our nucleophilic addition discussion, and indeed the entire core carbonyl discussion, by looking at some thermodynamic data for the nucleophilic addition associated with the simplest aldehydes, methanol and ethanol, and then the simplest ketone, acetone here. First of all, let's think of the hydration reaction. We're going to look at the equilibrium constant of the hydration reaction. So when you have methanol here, right, the smallest, the simplest carbonyl compound, whether you do it in acidic or basic solution, pretty much the equilibrium is over on the right. Very large equilibrium constant, which means that most of the product is present, that most of the species is in the gem diol form. Then you get down to ethanol, and the equilibrium constant is 1. In other words, if you take an aqueous solution of ethanol, about half of it will be in the form of ethanol and half of it will be in the form of the gem diol. And then you get down to acetone, and the equilibrium constant really small, really towards the acetone. In other words, hardly any of the acetone has reacted to make the gem diol. So when we're looking at hydration and the equilibrium constant, the really small methanol reacts a whole heck of a lot. The bulkier acetone hardly reacts at all. Now, even though thermodynamics and kinetics are separate species, you see that same trend for the rate of the hydration. Okay, the very little bit of the acetone that doesn't react reacts really slowly. However, the quite large amount of the methanol that reacts very quickly. So the reaction is favored heavily to the products, both in terms of speed and the extent of the reaction. And seeing as how we started with the cyanohydrin reaction, I'll show you the equilibrium constants for that match up the same thing. Okay, the very small methanol reacts really quite significantly at the equilibrium. Just about everything, 450,000 to 1, is in the gem diol. When we get down to the acetone, there's still more of the acetone has reacted with the HCl, but significantly less than ethanol or methanol. Now, what we're seeing here are two important issues. First of all, a steric issue, bulk around the attacking site, and I put that in pink to go along with the relative rates, because bulk tends to be a kinetic issue. If the attacking group can't get in to react, that's going to affect the reaction speed, okay, because what it's saying is that you've got to have a massive energy boost for it to force its way in. So if you think about a group attacking this slightly positive carbon, very easy to get in here when there's two hydrogens in the way. Harder when one of those hydrogens is replaced by a methyl group. Much harder when both of them are methyl groups. So the fact that as you get bigger groups here, you're going to make it harder for a reaction to take place. You see that in terms of the kinetics, a much slower reaction for the bulkier groups. But then we also have to think about electronic issues and inductive effects. Now, we talked about this a little bit, and I'm going to bring it in as we go through. But essentially, a hydrogen has got absolutely no effect on the carbon to which it is attached electronically. But methyl groups are pushing electrons towards the carbon. They have a positive inductive effect. They're pushing electrons towards. If I had an electronegative atom here, it'd be pulling electrons away. But methyl groups push electrons towards. Now, seeing as how the reactivity of this carbon is based around it being slightly positive, well, if you've got something pushing electrons towards it, you're going to make it not as positive, and if it's not as positive, it's not going to react to the same extent. And we see this with the equilibrium constants. Okay, the methyl groups push the electrons towards the carbon, thus making the carbon less reactive. This is a thermodynamic effect, so inductive effects are thermodynamic effects. And so what we see is that where you've got no methyl groups, nice and reactive, one methyl group, less reactive, two methyl groups, even less reactive. Now, if you take this a little bit further, what you'll realize is that when it comes to bulk, you always have a hydrogen in the aldehydes, regardless of what the rest of this group is, you always have 2 non-hydrogen groups there. So aldehydes are less bulky than ketones. That makes them more reactive. And also, when we think about inductive effects, aldehydes always have 1 ketone that's not going to do anything. Ketones are going to have 2 alkyl groups here that generally, if they're just straight alkyl groups, are going to be pushing electrons away, making the carbon less reactive. Thus, no matter how you think about it, aldehydes are more reactive than ketones. Now, I want you to bear that inductive effect issue in mind, and we'll have a little question at the end of the worksheet associated with that. Anyway, here for now is the end of our module on carbonyl compounds, naming, physical effects, synthesis, and reactivity, with some structural considerations thrown in there. Hope you enjoyed it.